Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on August 23, 2025, just 3 days ago. The striking result is that attention outputs live in a surprisingly low-dimensional subspace, where about 60% of directions capture 99% of the variance, and this geometry creates many dead features in sparse dictionary learning. The paper is titled, Attention Layers Add into Low-Dimensional Residual Subspaces, and the implications for model training are quite significant. The study traces the low-rank effect to the attention output projection matrix, then shows a simple subspace-based initialization that slashes dead features and boosts reconstruction. Alright, the feature tweet echoes the low-dimensional attention claim, linking it to why sparse autoencoder features go dead, then credits active subspace initialization for reviving them. Engagement looks solid, with roughly 289 likes. Alright, the tweet highlighted the core claim, and Figure 1 now illustrates it visually. The diagram shows attention writing into a narrow active subspace of the residual stream, which means most variation lies in a few directions. The right panel depicts a learned dictionary where features aligned with the active subspace stay alive, while features pointing outside that subspace turn dead because they rarely receive signal. This mismatch explains why random initialization wastes capacity, so aligning features to the active subspace becomes crucial. The earlier tweet set the claim. Figure 1 now shows the evidence across layers, model families, and datasets. The red curve for attention output sits far lower than the green MLP output, and the blue residual stream, which means the attention right occupies a much smaller intrinsic dimension. The definition uses singular value decomposition so that 99% of variance is captured with fewer directions. The consistent gap across all three panels signals a universal low-rank pattern, not a model-specific artifact. Okay. The previous figure set the intuition. Figure 2 now quantifies it. The left panel shows a much sharper spectral drop for attention output, which signals that only a small set of directions carry most variance. The right panel reports loss recovery, and attention reaches 95% with roughly 1/4 of the components, whereas MLP and the residual stream require far more. Together, these curves confirm that attention writes into a compact subspace that is highly efficient for downstream performance. Okay. The previous figure quantified low-rank effects, and Figure 3 explains why. Figure 3 shows a variance decomposition along principal components, separating the contribution of the concatenated head outputs Z from the projection matrix WO. The red curve tracks Z at the head of the spectrum, which means early components are supplied by the heads, while the cyan curve drops sharply in the tail because WO suppresses those directions. The takeaway is that anisotropy in WO compresses the output into a lower dimensional subspace. Alright, the previous figure explained how the projection compresses attention outputs. Table 1 reports the practical impact for a sparse replacement model, with active subspace initialization cutting dead parameters from 68.4% to 40.5%, and slightly lowering normalized mean squared error from 0.130 to 0.121. This improvement matters because fewer dead parameters mean more capacity actually contributes to reconstruction. The numbers suggest that aligning with the active subspace stabilizes training and yields better accuracy with the same hyperparameters. Okay, tying it together, attention writes into a compact residual subspace, and that geometry explains widespread dead features in sparse autoencoders. Active subspace initialization, which seeds features inside the dominant principal component subspace, revives features and improves reconstruction, especially with sparse atom. Principal components are directions capturing maximal variance. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.